Okay, hello everyone. Welcome back. How's it going? Good, good. Everyone is still alive. Okay, so today I'm going to continue our discussion of higher form symmetries. So most of today is going to go into a discussion of SUN gauge theory. I'm going to explain what the one form symmetry is for SUN gauge theory. That's pure SUN gauge theory. I'll explain what happens to it when you add charged matter. And I'm going to do this in a few ways. I'm going to first start by doing it using this continuum action. And then we're actually going to go to the lattice, because I think that is the cleanest way to understand why these symmetries exist. And then we'll see how we're doing with time. I would like to discuss the effective theory for a spontaneously broken Zn higher form symmetry. That turns out to be a topological field theory, and I'll explain why and what it is. If I have time, I want to talk a bit about the sort of simple lattice gauge theories, like the Z2 lattice gauge theory. That's in many ways the simplest gauge theory, and you can see things very transparently there. I'm not so sure I'll have time. We'll see how we go. Okay. So to remind you where we were last time, what we're doing is we are looking at SUN gauge theory, whose action is this in the continuum, and I remind you that the gauge field A is valued in the Lie algebra. So it's valued in the Lie algebra of SUN, but the properties I'm going to talk about actually depend on more than the Lie algebra of the gauge group. They actually depend on global properties. In particular, they depend on what's called the center of the gauge group. The center of the gauge group is the part of the gauge group that commutes with everything else in the gauge group. Okay? So for SUN, the center is generated by matrices that look like this. They're diagonal, and they're just the overall phase, okay? Each of the 2 pi I k over n, where k goes from 0 up to n minus 1. This clearly commutes with everything because it's diagonal, okay? It's also in SUN because if you take the determinant, there are n factors, and that cancels the n in the denominator. So you end up getting 1, okay? That's important. So this is clearly the group Z sub n, all right? And now the statement is that the one form symmetry of SUN gauge theory, SUN Yang-Mills, is Zn. Okay? Some of you know probably about something called the center symmetry, which clearly involves many of the same words. That is a slightly older way to think about this one form symmetry. All right? The modern way of thinking about this one form symmetry is what I'm going to tell you today. All right? And I'll make the connection to the slightly older thing in a bit. Now, are there any questions about all of this before I keep going? Everyone happy? Okay. So now to tell you about a one form symmetry, what I have to do is show you two things. I have to show you the charged operators, who are going to be line operators. And almost more importantly, I have to show you that there exist topological surface operators who measure the charge. Okay? I'm going to start with the line operators. I did this last time basically already. I'll just remind you. So the charged line operators are, of course, the Wilson lines. Close the brackets? Yes, okay. So the Wilson lines are labeled by a closed curve C, okay, and a representation R of the gauge group. So R is some rep of the gauge group, which in our case is SUN, okay? Now, it turns out that the one that we want for this purpose is going to be R in the fundamental. Okay? That is the R that we want here. The physics of the Wilson line is different for every R. And what I'm saying will be different for every R. The simplest one to think about is the fundamental rep. As you'll see, it will not work for other reps. It will not work for the adjoint rep, okay, for example. It will work for the fundamental one. Okay. So this is unsurprising, I think. This is really the natural line-like object, so it makes sense that it appears as playing a role. The more interesting thing, the less obvious thing I would say, is really what is the 2D surface operator? So it's 2D because we're at 4 dimensions. what is the 2D surface operator that is topological? Okay. So this is called the Gukov-Witten surface operator. And I'm going to call it G sub G, and as always, it depends on some codimension 2 manifold, so some 2-dimensional surface, okay? So we're going to interpret this G sub G, and what is little g here? This capital G is for Gukov, I guess, okay? And the little g is an element of the center, okay? So little g here is an element of Z sub n in this case. So is there a question? Yeah. 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 I'll show you. It's not correct to say it doesn't work in any other representation. It turns out to depend on something called the n-ality, which is sort of, I think it's 1 for the fundamental and is basically 0 for the adjoint. It will be pretty transparent, to be honest, by the end. I hope by the end of this. Yeah, yeah. So you can see what it works for and what it doesn't. Yeah. Good. Other questions? Yeah. When I say it doesn't work, I mean it will not be charged under the symmetry. That's what's going to happen. I say it doesn't work. Yeah. You can, of course, always study it. Yeah. Good. Other questions before we keep going? Okay. So my Gukov-Witten surface operator is labeled by little g, where little g from now on will be an element of SUN, so it's going to be one of these matrices. Okay? And of course, this makes sense. I mean, the symmetry, the things that generate the symmetry are labeled by this elements of the symmetry group, right? Okay. Now, what is the Gukov-Witten surface operator? So I'm going to do this in 2 ways. I'm going to first give you the standard argument that's given in the continuum. Okay? And we'll see that this is fine, but maybe you want something a bit more tangible. We'll then go to the lattice gauge theory, where you can do this very explicitly as a UV regulator, and I'll show you a slightly different argument on the lattice gauge theory. Okay? Okay. So first, in the continuum, the way we define this Gukov-Witten surface operator is the following way. So in the continuum, what you do is you say that to insert G sub G, so to insert the Gukov-Witten operator into the path integral, we demand so this is defined on some surface M2, right? So here's some surface. We demand that the integral, the path-ordered exponential of the integral of A, in other words, the holonomy of the gauge field on some little circle, sorry, this should be S1 that wraps M2. The path-ordered exponential of some integral of A around the surface, okay? So I'm integrating A around this surface, like this. I demand that this is equal to G, an element of the center. Okay? This is a demand that we make in the path integral. So note, this is also an example of these disorder operators. Okay? So just to stress again, to insert this into the path integral, you do your path integral over all your fields, but you do them subject to the constraint that the integral of A around this surface is equal to G. Okay? This is a perfectly fine response to make, a question to make. And I should stress, actually, this is done over a small S1. Okay? Over an infinitesimal S1 surrounding this surface. Yeah?
Actually, I had this thing before, the discussion before. So, is it possible that we impose that condition in the path integral to use a local multiplier?
It is, but it's So your question is a good one. It is getting into the guts of what this constraint really means. And I'll be honest, this is what we say in the continuum. I find it a bit unfulfilling and difficult to implement. And that's why we're going to do it on the lattice in a second. On the lattice, it'll be very explicit what we're doing with this. And in fact, on the lattice, the condition is morally similar to this, but not exactly the same condition. Okay? So maybe we can come back to your question in a little bit. It's a very good one. The point is that the truth is, calculationally, I'm not so sure I know how to actually do this in any actual calculational way in the continuum. This is really related to your question. Like, I think in principle you could try, but if you think about it, it's really quite singular, the Lagrange multiplier you'll be using. And so let me come back to that. It's an excellent question. Yeah. Yeah.
When you're talking about disorder operator,
Yeah.
disorder in what sense?
Yeah, I mean, this is a good question. It's a name, first of all. I think that the reason why it's called that is because when you're doing statistical physics, then sometimes you have order parameters, right, which are it's just a field. It's just like phi, okay? And this is like the opposite of that. It's not the field phi, it's some boundary condition in the path integral. When it has a vev, then it means that the other thing that you normally had does not have a vev anymore, and so it's sort of like disorder. I think that's the idea behind the name, but it's just a name. Yeah. By disorder operator, I just mean that it's defined in terms of boundary conditions in the path integral. Yeah. Good. Other questions? Okay. So this is it. Okay. And of course, now if you think about this, you can define this really for other group elements too, right? I mean, this idea works for any element of the gauge group, right? It only works up to conjugation because you see this object transforms in a gauge transformation, it transforms. There's no trace here, right? So it actually transforms by U dagger under a gauge transformation. So in this case, U dagger come together and go away. But in general, if you pick some other group element, you could define it up to conjugation by group things, and you could study this, and it's a thing people do. But it's only topological if you take this G to be in the center. Okay? So if G is in the center, which it is, then it's topological. Okay. Okay. Now I'm going to try to prove to you that this is topological. Okay. I've not done that yet. I've just told you this is a thing, but the whole fun is to show it's topological. So how do we see that? So what is happening here physically? Physically, what this thing is doing is it's creating a field which things that move around it can feel, right? This is a field that everything that goes, all the degrees of freedom that are living their life everywhere can feel that, right? And the question is, how do the degrees of freedom that are present in the gauge theory, how do those degrees of freedom feel this, okay? So the way in which anything feels a gauge holonomy is, again, through a Wilson line, right? So let me first figure out what happens if you have a fundamental Wilson line, all right? Okay. So this works in the following way. So imagine you have a fundamental Wilson line. So imagine you have W of F. F is the fundamental representation in that formula, okay? So I have W of F on some curve C. All right, so this is a 1D curve. Let me draw a bigger picture here. So I have W of F on some curve C. Here's C. Okay, and here's my Gukov in M2. And I want to ask, actually, I drew this picture poorly. Try again. I realize this is not the topology that I want. I want the other topology. I could have just relabeled it, but okay. So doing it the other way. Okay. So here's my Gukov surface operator. Okay? And I want to ask what happens if I take this guy, and let me make this M2 be an S2. I want to ask what happens if I take my Gukov surface operator and pull it through this curve C. Okay, that's the game that we always play. So I want to ask what happens there. All right? Now, this is a bit heuristic now, but bear with me and we'll do it properly in a second. So what is this thing doing? What you want to do is imagine what happens when you take the Wilson line through here. Okay, so I'm going to zoom in at this part here. We're about to drag the Wilson line through this surface operator. So if this is the Wilson line, here's the bit this is the part sort of tangential into the page, is the Gukov surface operator. So my Wilson line basically is now, in one case, is going around this thing, and in the other case, is not going around this thing, right? That's what's happening. I'm dragging it through. And so the difference between these two cases is basically the Wilson line going just around the operator itself. Okay? Does that make sense? This picture that I'm drawing here? And we know what this is. When the Wilson line goes only around the operator itself, then the whole point is that's equal to G, right? So in other words, what this object does is, in the trace in the Wilson line, which is a product of many different things, it inserts an extra factor of g at the point where you're doing this intersection. Okay? That is the point of this thing. Now, this is in general somewhat confusing because this is a non-abelian Wilson line, so of course inserting one group element somewhere is a weird thing to do. It seems like it depends exactly where you insert it. But here, of course, we're saved by the fact that it's in the center, which means that it commutes with everything else. So it really doesn't matter where the insertion happens, it just inserts a factor of g in there. Okay? And this is why this only makes sense when you're in the center. Right? Okay, that was a lot of words. Let me now write down a formula. The formula for what I just said is the following, that if you drag this thing through here, you pick up an overall phase, and that phase is going to be the trace in the fundamental of this group element. Okay? It's in the fundamental because that's that fundamental, so it's the trace in the fundamental. Then you should divide this by the trace in the fundamental of the trivial group element. This is because the trace in the fundamental will pick up a factor of the dimension of the representation, which is not what we're going for. We're trying to just get the overall phase. Okay? So we should divide by that. And then this thing multiplies what is left in the Wilson line. Okay? So I've given a reference for this formula. If you look in the notes, there's a reference that has some more words. The words are basically the words I'm saying right now, though, but it's nice to see them written down. Okay? Okay, does that make sense to everyone? This thing here just captures the overall phase that I talked about in here, and this is the thing left over. All right? Okay, and then what is this? Let me just finish writing this down. If I take the trace in the fundamental of that group element, I of course just get n times each of the 2 pi I k over n. This gives me n, so the n's cancel, and I just get the overall phase in the end. So let me write down the rest of the formula. S2 Wf of c equals 2 e to the 2 pi I k over n Wf of c. Okay? So this is what we find. This is what happens if you take the equivalent surface operator and collapse it on a fundamental Wilson line. It picks up an overall phase. Okay? Okay. So this is what we want for a Zn symmetry. We've seen this formula before, okay? But I stress that in this calculation, this Wilson line is an external object, okay? I'm inserting it into the theory. There are no degrees of freedom that are actually in the fundamental, right, in this gauge theory. All the degrees of freedom that are actually in the gauge theory are in the adjoint. So this is how an external probe sees the group of wooden surface operator. So here W of F is an external probe. We can now ask, do the dynamical degrees of freedom see this operator or not? Okay? So do the dynamical degrees of freedom see this? And what are the dynamical degrees of freedom? Well, I mean, they're basically the gluons, right? These are the gluons, and the gluons are in the adjoint, all right? So what I should really ask is, if you have an adjoint degree of freedom running around, living its life, moving around this operator, does that see it? So we should repeat this calculation for an adjoint Wilson line. Okay. And now this comes back to the question that some people asked. Is the adjoint Wilson line charged under this? Well, if you do the calculation again, okay, so what we're doing is we're looking at having an adjoint Wilson line now. Okay? And this turns out to be, of course, trace in the adjoint of the center element divided by trace in the adjoint of 1. Okay, now what is the trace in the adjoint of the center? The trace in the adjoint of the center is trivial. Okay, let's explain why that is. How does the group element act in the adjoint? If you have some matrix M that's in the adjoint, then the way that M transforms under a gauge transformation is this, right? This is the definition of the adjoint rep. Now, of course, if you take this to be the center, though, we have G, M, G inverse, or G dagger. And because it's in the center, then you can just pull this through here, and it goes to M, right? So in other words, the adjoint does not transform under the center. Okay, this is, again, just a well-known fact, all right? And therefore, the trace of the adjoint, of any center element in the adjoint rep is just 1. Okay, or rather, 1 times the dimension of the adjoint representation. Okay? In other words, this is now equal to this, and so we get this. And the reason why this happens is that the center G does not act on the adjoint representation. Okay? Okay. So people, I realize I didn't ask for starting. People are happy with this level of group theory, right? The adjoint fundamental. Okay, most people are nodding. If you're not, it's not a big deal. Just the point is just that the gluon degrees of freedom do not feel this guy. They do not feel a phase from this Krukov-Witten in-surface operator. Okay. So what that means is none of the dynamical degrees of freedom can see the surface operator. You know, the surface operator creates a phase, but nothing can see it. It's an invisible phase. And therefore, GG of M2 is topological. Okay? And therefore generates a Zn one-form symmetry. That's why we have a Zn one-form symmetry. Because this little g is in Zn. Right? Okay. So this is the continuum argument. All right. Now, to be completely honest, I don't find this. Okay, this is what's written in the literature. It's certainly true, but there are many things you could worry about here, to be completely honest. Because, I mean, okay, sure, maybe these Wilson lines don't see it, but you know, there's some short distance stuff happening when you get close to it. Is it really clear that you can regulate it in a way to not worry about that and really make it topological? You know, there are things that one could worry about here, all right? So what I'm going to do next is I'm going to redo this argument in a lattice regularization of the gauge theory. Okay? Yeah. Yeah.
You mentioned center symmetry.
Yeah.
If I remember it correctly, it's
Yeah.
connected with when you have a compactified circle in
Correct.
one direction. So can you make a comment?
Yes, no, excellent point. Okay, so there's something called the center symmetry, which, as you pointed out, is a symmetry that you get when you compactify things on a circle. So let me just tell you what the old center symmetry is and how it's connected. So imagine that you have a one-form symmetry, okay? But suppose you also don't know the words for one-form symmetry, and you want to make this into a normal symmetry that you know, a zero-form symmetry, because you know about zero-form symmetries. What you should do is take this theory and compactify it on a circle, okay? Because then, if you compactify it on a circle, then the Wilson lines wrapping that circle will appear as localized operators in the remaining dimensions, right? And you know how to do symmetries on localized operators. So this is actually how this symmetry was first understood. People always studied it when you compactified it on a circle, in which case the one-form symmetry becomes an ordinary zero-form symmetry in the non-compact directions. I claim you just don't need to do that. You can think about the one-form symmetry by itself in non-compact dimensions, okay? That gives you some extra conclusions that you could not have gotten from the old center symmetry point of view, all right? But you can always just dimensionally reduce and get this. So that's why this is, in the center symmetry, that's whenever someone says center symmetry, they really just mean this one, but they usually mean compactified, okay? Excellent question. Good, other questions? Okay, so, so now we're gonna go to the lattice, all right? So let's do this. So I'm going to now quickly formulate SUN gauge theory on the lattice. Okay. Can you raise your hand if you've seen this before? SU engaged triangle lattice? Okay. Some people have. Okay, good. But most no. Okay. So this is, to be honest, just a beautiful thing in its own right. Okay. Because the way that we calculate in the continuum, I mean, it's really horrible, right? Like we fix a gauge, all this beautiful stuff, and we fix a gauge and we treat this thing like a bunch of photons with an extra index. It's a horrible thing to do, okay? And formulating it on the lattice is just much nicer in many ways, okay? So, okay, so let's do this. What you should imagine is consider a hypercubic lattice, okay? So we're in 4 dimensions, so you should imagine a 4-dimensional lattice Z4, okay? This is a discretization of 4-dimensional Euclidean space, okay? Okay. Now, the basic degree of freedom in lattice gauge theory is defined on the links of the lattice. All right? So here are my lattice sites. I'm going to label my lattice sites by I and J and so on, okay? And then we also have links of the lattice, which I'm going to label by L, all right? And the orientation of the link matters, all right? So you should imagine there are arrows on all these links, and if you were actually calculating with this, you need to have a convention for picking those arrows, but I'm just going to try to avoid it as much as I can, but they're oriented links. They each have an arrow on them. Now, I'm going to use a notation where L is a link, and if I write ij, this means the link from I, site number I, to site number j. Okay? So here, this link here is link ij. Okay? These angle brackets mean the link from I to j. So I'll only use this when sites I and j are right next to each other. Okay? Okay, good. Now, this is the kinematics, this is the setup, okay? And now in lattice gauge theory, the basic degree of freedom is an SUN element, or a group element in general, on the link. Okay? So on every link, we have a group element. U sub L. Okay? So this is crucial. The degrees of freedom live on the links in pure gauge theory. Okay? So we can write it as U sub L. And reversing the orientation of the link inverts the operation of the group. In other words, if I use this notation, Uij, which is fine, this is U living on this link here, the one from I to j, this is equal to U dagger ji. Okay? That's why they're oriented. Okay. Okay. Now, what are gauge transformations? So gauge transformations are labeled by an SUN degree of freedom, so an SUN function, not on the links, but on the sites. Okay? So I'm going to call that lambda sub I. And under a gauge transformation, the way that my variable ui transforms is like this. Ui goes to lambda I, uij, lambda j dagger. Okay? So just to stress, lambda I is an SUN at every site. And the way in which a link element transforms is, on all of the sites, I have some lambda, and this U transforms as lambda coming from here and lambda dagger coming from here on the other side. Okay? This should seem really nice, right? Like this is very nice and geometric. You can see it makes sense for you to live on the links, so this kind of thing is possible. Okay? So morally speaking, to make the connection, or not even that morally, to make the connection with the continuum, you see U is like a tiny little Wilson line going from here to here, okay? So in other words, the way to make the connection with the continuum is U sub ij should be understood as being the exponential of the continuum gauge field going from site I to site j, okay? This is, morally speaking, what this thing is. Does that make sense to everybody? That's why it transforms like this. Okay. But this is, I stress, this is to make the connection to the continuum. Here, A is the continuum gauge field. We're not going to use A. We work with U. Okay. Okay. So the next thing we have to do is to figure out how to write down an action. Okay. So for the action, we need a field strength. So we need to next write down the analog of the field strength in this lattice gauge theory. All right. Now, the field strength in the continuum is a 2 form, which means that it's sort of actually associated with a plaquette. Okay? A plaquette of the lattice, meaning one of these little squares is a thing that had a sort of two directions, and so therefore a plaquette is associated with the field strength. And so now we need to figure out how to construct a sort of gauge invariant object that lives on the plaquettes. All right? And the way to do that is, so here this is going to be my field strength. I'm calling it W. All right? And W is the following. It's the trace. You can use whatever rep you want, but I'm going to take it in the fundamental. This doesn't matter. Of a product of all the links living in the plaquette, U sub L. Okay? And here, this product is taken in an oriented manner, which means that sometimes you take U and sometimes you dagger, depending on how you're going around the plaquette. Okay? So again, let me draw a picture of this. Okay? I'm drawing the lattice over and over again, but I guess it's okay. It'll get too cluttered otherwise. If you want W on this plaquette, what you do is you take a product of this times this times this times this. So take the product of the group elements living on all of these 4 things, okay? And then take the trace. All right? Does that make sense to everybody? Okay. This is gauge invariant, right? So this is gauge invariant. And you can see why, right? So there's a lambda living on each of these sites. There's a lambda gauge transmission living here. But when you multiply this guy with this guy, then the lambdas coming from that thing will cancel. All right? And it'll cancel, and it'll cancel, it'll cancel. And because it's closed, they'll all cancel in a loop, and it's all fine. Okay? So this is the analog of the field strength. All right? In my notes, I have this worked out in detail in the xy plane, but you get the idea. Let me not work it out. You understand. Okay. So this is a number, okay? So given some configuration of the gauge field, this is just a number. And with this number, we can now form an action. All right? So what is our action going to be? So the action, this is called the Wilson action, is the following. It's minus 1 over g squared, sum over all of the plaquettes, this is the action of lattice gauge theory. Okay. You sum over all of the plaquettes in the lattice. From each plaquette, you take this trace of Wilson line things, and you have to add its dagger because generically it's going to be a complex number. Okay.
There is no square or something.
The square is kind of in here already. The square is sort of in there already. So that's a good exercise. What you should do is a good exercise to do. So this is also in the notes. Is to plug this into here, plug this into here, and then show that the square is kind of in there already. Okay, that's a good thing to do. Yeah. Basically, the linear, this object contains things to all orders in A, and the linear part cancels when you take the trace, basically. That's really what's happening, okay? Okay, good. Any questions about this? Is everyone happy? This is a whirlwind tour lattice gauge theory, yes?
Just on the last
Yeah.
sentence,
Yeah.
does it contain all orders of A because I have an exponential of A?
Yeah, that's right, yeah, exactly. So if you try to, so there's an exercise again, again, I'm not going to get to do all these exercises in the tutorials, but there's an exercise in the tutorial, in the notes, which is to expand this and show that to lowest order, this thing gives you the normal Wilson action, normal Yang-Mills action, F square, but because it's to all orders, you get also higher derivative terms, F cubed, probably not F cubed, but F to the fourth, blah, 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 and so on, okay? So, okay, good. So, now, this is the action, and to make this thing complete, I should tell you how to construct the partition function, okay? So the partition function is what you get if you path integrate over this action. So what is Z in this theory? Ah, thank you. Yeah. Yes?
Does this also work for U1 theory?
Yeah, absolutely. Yeah. This works for any, I keep saying SUN, this works for absolutely any group, okay? So if we have time, I'll do it for Z2, which is really the simplest. But for U1, it's actually quite nice. This just becomes a sort of cosine of it's like cosine of A minus A, stuff like that. It's really very simple. I recommend working out U1. It's quite fun. Yeah, good. Yeah. This all works for absolutely any group. Okay. Sometimes this is equal to this, but that's fine. Yeah. Okay, good. Now let's work out what the partition function is. The partition function is what you get if you now path integrate over this field U, okay? So what you do is you just do the integral over all U's, okay? And this is the partition function. Now, this partition function is in many ways simpler than the thing in quantum field theory, because you see, this is just discretely many integrals, right? 1 integral, 2 integral, 3 integral, 4 integral. You don't need to worry about what, when I say path integrate, I don't really mean path integrate, I just mean do this discretely many infinite integrals. So this is a very tractable thing. You can really put this on a computer. It's a very good thing to do. You can really calculate properties of life from putting this on a computer. It's extremely well defined, okay? I've not told you how to do an integral over a group element. There exists a measure for doing the integral over a group element, something called the Haar measure to integrate over U. This is to integrate over a single du, and basically, if you have a group, you can define a sort of you can define an invariant integration measure over that group. That's really just because the group has a geometry coming from the fact that points next to each other are close to each other by the Lie algebra, and so this is really what you think it is. It works out in a sort of standard way. Okay. Okay. Good. Now we are now ready to use this to try to do something. And what we're going to do is we're going to now construct all the objects that we did in the continuum on the lattice. All right. So first, the Wilson line. So the Wilson line is defined on some curve C, right? So the Wilson line in some representation R is really just what you think it's going to be. It is the trace in that representation. And now, if I have my lattice, and I pick some curve in it, okay, then that curve, of course, just intersects lots of links, L1, L2, L3, blah, 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 blah. And it's just the product of the links in that curve times U sub L. Okay? This is the Wilson line. All right? This is really why I called this W sub box here. It really makes really clear the field strength is just an infinitesimal Wilson line. Okay. Okay. And now we need to go to the Gukov-Witten operator. All right. Good. I'm actually doing okay on time for once. So to do that, I'm actually going to need a lot of boards. So I'm going to start erasing the boards now. Any other questions as I erase them? While I erase them, I encourage you to expand this out in powers of A and convince yourself that that is the continuum action. Yeah,
the
yeah.
continuum ones only have like f squared.
Yeah.
And now you say if we expand this, we get higher curvature terms.
Yeah, yeah, yeah.
Are these then somehow weighted by the lattice spacing such that in the continuum limit they vanish?
They are weighted by the lattice spacing. Yeah, that's correct. To go from here to here, I have this integral from I to j. That really means that there's a notion of length appearing here. So I have to say something, I have to connect this sort of abstract computer science thing to physics by putting a length a here, and then there's a factor of e to the I little a lattice spacing times that. And then if you work it out, then indeed they're suppressed by the lattice spacing. That's correct. Having said that, I don't know if it's, they're irrelevant in some sense, but I think people still worry about them. Like there's refinements of this lattice action to try to get those things to go away. You could add like W box squared, right? Why not? And then that will change the coefficient of those terms. And I think there's still a game people play to try to get those to go away. So you can do various things, yeah. Sorry. Yeah, good question. Yeah. Because we are just trying to get like conceptual stuff right, we're just not going to worry about that at all. Yeah. Yeah. Oh, sorry. Another question? Yes, Pablo. Yeah.
Like, I don't know if I'm correct in this, but if you then close the line and you form a Wilson loop,
Yeah, that's right. Sorry, what?
you obtain the field strength?
The first term? The fields, yeah, you do. You obtain the field strength. So,
Yeah, that doesn't
yeah.
kind of match the intuition I have about the continuum theory, right?
Which part does it not match?
Like closing a Wilson loop
Yeah.
and then obtaining exactly the field strength.
Yeah, yeah.
Which is somehow the derivative from the Wilson loop.
Yeah, so I think that's okay. It's like if you have let me just do this here. You can see this here. If you have integral of a over some closed loop, then that is equal to, let's do the abelian case, okay? Then that is of course equal to the integral of f over the thing that fills it in, right? Because f is dA, these two things are actually the same. This is the idea, okay? The integral of a over a tiny closed loop is equal to f times the area of that loop, okay? And because we're doing it on the lattice, there's no length scales present here. But if you put back the length scales, you'll see that this is what happens. Does that make sense? Yeah, good. Yeah, indeed. Yeah. The key intuitive thing is that on the lattice, everything is an integral. You see, they're not objects at points. They're little integrals of the continual fields times geometric elements. Oh, whatever.
And before you erase it, how do you understand the action? Because like you use endpoint W squared term, and I was expecting you to write down W squared.
Yeah, yeah.
There's an F squared in the
Yeah, if you expand this out, which is a thing that it's really just a thing exercise, you'll see that you just get the leading term is indeed an f squared from this. Yeah, it's kind of because every term possible appears, but the f term is just the trace of an f term is going to be 0 because a single algebra element vanishes. Yeah, so that's really what happens. Everything appears, and the leading term is an f squared that survives. Yeah, it's a good thing to do. I've not done it in many years, to be honest, but I might do it in real time in front of you guys in the tutorial if people want to. It's in David Tong's gauge theory lecture notes. He does this quite explicitly. So I should say that most of the notation in this section up till now, the notation that I use is taken directly from David Tong's gauge theory notes. So, which, as always, are a wonderful place to learn about anything. Did I forget? I think I forgot to squeegee this one, right? Distracted by the questions. Okay. Okay, good. So now let's come back to so we've created the Wilson line. And now we need the Google Witten guy. Okay? So to get the Cook of Witten guy, I want to point out that the action that we just defined, it sort of has a natural slot to put in a Zn center element. Okay? Let me explain to you what I mean by natural slot. Okay? So the Wilson action, so the action that I've erased over there, it has a natural slot for putting in a Zn element. So first of all, consider a Zn function on the plaquettes. Okay? So I'm going to call this B sub plaquette. And B sub plaquette associates with every plaquette on the lattice a Zn element. Okay? Now, there is a way to incorporate this B sub plaquette into my lattice action. And that is the following thing. Previously, when I worked out my W plaquette, I just took the trace of all the Wilson line elements, trace of all the group elements in a little plaquette. And notice I can do the following thing. I can take the trace, my notation is getting a bit tortured here. This should really have both the plaquette and the R, but you get the, let me ignore that. It's the trace in the fundamental of B sub plaquette times the product of L in the plaquette times UL. Okay? So this is a geometrically natural thing to do. So I have my links, and I have my B sub plaquette. You should imagine B sub plaquette lives in the inside, and the U's live on the outside on the links. And so when I'm evaluating W on a plaquette, I take the product of these things and also multiply it by B before taking the trace. Okay? Because B is in the center, it doesn't matter where I put this B in this product. Okay? Notice that if B was not in the center, then this geometric idea kind of would break down, right? Because if B was not in the center, you'd be like, well, do I put it there? Do I put it there? Where do I put it? But because B is in the center, I can really associate it with the plaquette in an unambiguous way. All right? It's crucial that B is in the center for this idea to work. Okay. So this is a sort of a twisted field strength. I have sort of twisted this product by this B. Okay? Okay. And now, what is B? You should imagine B is an external source. Okay? I can do everything in the presence of B. So B is really an external source. All right? And of course, in particular, I can now define my action in the presence of B. So that is, again, sum over the plaquettes. Oops. Minus 1 over G squared, sum over the plaquettes. Dagger. Okay. So this now depends both on U and on B, the action. And I can also construct my partition function. I can construct my Z, which is a function of B, by doing the path integral over all the U's in the presence of this action. Okay. So I should erase that. Okay. So you can see where we're going with this, right? B is basically a Zn source for this Zn one-form symmetry. Okay. That's the role of B in life. So now we are pretty much ready to define the Group-Witten operator. But to be honest, I think this is actually, before I get into that, because I need to draw a bunch of cubes and stuff, I think this is actually a good time to take the break. Let's take a break now and reconvene at 10:30, and I'll practice drawing cubes in the meantime. Okay, welcome back. Previously in higher form symmetries, what we just did was I showed you how to couple a source, a Zn valued source defined on plaquettes, to this non-abelian gauge theory action. Okay? And I just stress it's crucial that it's Zn valued. If not, I don't know how to write down that first term. It doesn't really make much sense. Okay? Now what I want to do is so the truth is, you can already kind of see that the fact that this source exists and transforms in some nice way, as we'll see in a second, it already sort of implies the Zn symmetry is there. Okay? But to close the circle, I now want to use this to construct the Group-Witten surface operator. Okay? So let's do that. I erased something. So first of all, there was the Wilson line. So what was I going to do? Right. Sorry. So I erased the partition function, but let me write that down again. The partition function is just the integral over all of these things. Is it okay? Thanks. All these things in the presence of this source. Okay? So I have some Zn valued source on the plaquettes. I integrate over all the group elements on the links, and I get some functional of that source. That functional is Z of B. Okay? That functional depends on the source. Okay? It's a fact. Now, to define the Group-Witten surface operator, so to define G sub G as a function of M2, what you have to do is, first of all, I want to do something which works as on a 2D surface on the lattice. It turns out what you want to do is take M2 to be a codimension 2, 2 surface on the dual lattice. Okay? So what is the dual lattice? The dual lattice is a technical definition, but if you have a cubic lattice like what we have, then the dual lattice is just all the points that are in the middle of the lattice. Okay, that's the dual lattice. All right, there's a more correct definition that works for any lattice, but let's not do it. Okay, so this is the lattice. This is the dual lattice. Okay, they're offset by half. Okay, now. What we want is a codimension 2 surface on the dual lattice, all right? And it turns out that a codimension 2 surface on a dual lattice always intersects plaquettes on the original lattice, okay? So I'm going to draw a picture of this. I should probably have drawn it during the break, but let's try again. So I'm going to do this in 3D because that's the maximum that I can draw. So what I'm first doing is I am drawing the original lattice in 3D. Okay, so here's the original lattice in 3D. Okay, and now I'm picking a codimension 2 surface on the dual lattice. Okay, so first let me draw the dual lattice points. Here are the dual lattice points. Okay, each of these is exactly in the middle of each of these cubes. Okay, use your artistic, imagination, I guess is the word I'm looking for. And now a codimension 2 surface on the dual lattice. We're in 3D. So codimension 2 is actually a line and not a surface, okay? So a line on the dual lattice looks like this. Okay, so here's a line on the dual lattice. And the line on the dual lattice is clearly piercing plaquettes, right? It pierces each of these plaquettes, right? You can see that. So the point is a codimension 2 surface on the dual lattice in any dimension always intersects plaquettes of the original lattice. Okay? And this statement holds in any dimension. All right? Even though I can only draw a picture for 3 and also for 2. I mean, for 2 dimensions, codimension 2 is a point, and it clearly intersects a plaquette. That's a really simple picture. Okay. Everyone happy with this geometry? Okay, good. Now we can define the operator. To define the operator, what you do is you've taken M2 to be this surface intersects plaquettes. And now, for each plaquette that intersects M2, set B sub plaquette to be equal to G. Remember, G is the Zn element by which I'm defining this operator. Okay? So for each plaquette that intersects this thing, set the B, this source, equal to G. Okay? So G here, G here, G here, G here. Yes?
I just thought of something.
Yeah.
It was taking the 2D pictures you were drawing too literally earlier.
Yeah, yeah.
Is a plaquette always two-dimensional regardless?
Yes, a plaquette is always two-dimensional. Sorry, I never really defined plaquette. A plaquette is always two-dimensional. It's a two-dimensional face, okay? In 2D, it's this. In 3D, it's this. In 4D, yeah, you get the idea. Yeah, okay, yeah. Good. Other questions? Yeah. Okay. So for each plaquette that intersects M2, set B subplaquette equal to G, and the rest of the B subplaquettes set equal to the identity. Okay? Yeah.
Maybe one question, do I have to, when you define a plaquette, do I always have to do nearest neighbor, or could I do a diagonal split through one of these cubes?
No, I mean nearest neighbor. I mean exactly in this way. This is why I'm only doing it on the cubic lattice to avoid any weird diagonalness. You can do similar constructions on any lattice, hexagonal, whatever. The geometric structures actually work. It uses a more general geometric structure than cubes, but I just don't really want to. I can't think about them, to be honest. Yeah, so I don't want to define them. Yeah, good. Okay. Okay, so notice what we've done. I have taken the data that I have and done a manipulation in the path integral. Okay? And then this algorithm defines a B who depends on M2 and G in a particular way, right? The path integral in the presence of this source is equivalent to inserting the Gukov-Witten surface operator in the path integral. Okay? This is the definition of the Gukov-Witten surface operator. It is to do the path integral in the presence of the source defined in this manner. Okay? Does that make sense to everybody? So this is the definition of G. It is a fully constructive definition. This is extremely operational. You can really simulate this. Put this on a computer and work with this. Okay? Now, okay, I'll give you a second to just stare at this, because this is a slightly involved construction, but it's a very concrete thing to do. All right? Okay. Now, what I have not done yet is proven to you this is topological, right? I just told you how to do something. I now need to prove to you that this is a topological thing. In other words, it does not matter what surface you use, but this thing will stay the same, all right? So now let me do that. Okay. So to see that this is topological, let's see. Here. To see this is topological, let's consider trying to deform the surface. Oh, thank you. Okay. So when I have this surface, you see all of the action is really in the 2 dimensions that are transverse to the surface. So I'm just going to draw a picture of only those 2 dimensions. Okay? Let me ignore the other dimensions for now. All right? So if I'm only looking at 2 dimensions, then it looks like this. Okay? So to use the same colors as I used previously, what you should do is, I'm only looking at 2 dimensions. Imagine that my Gukov-Witten surface operator sits here. Okay? So that 3rd dimension is coming out of the page, and the 4th one I'm just not drawing at all. So it sits here. Okay? So in other words, I have a twist of my partition function by G at this point, right? Okay. So now the question is, can I take this and move it over here, for example? Right? If I can, then it'll be topological. So I can do that. Let me show you how. So if I call these group elements U1, U2, U3, and 4, the way in which this thing enters is that I take the product of U1, U2, U3, U4 times G, right? So now let's consider doing the following change of variables in the path integral. Let me take U4 and do the following change of variables. G inverse times U4. Okay? So what happens? I have U1, U2, U3, U4 times G, but after the change of variables that I just did, this G inverse is going to cancel this G, right? And so in the action, it will look like this G is no longer there anymore, right? So post change of variables, after doing that operation, U1, U2, U3, U4 times G inverse, there is no G here anymore. But of course, U4 also enters into this term in the action. And post change of variables, the G is going to appear here. Okay? It'll appear in the action as though the G is now living on this plaquette, whereas previously it was living on this plaquette. Does that make sense to everybody? How I can transfer the thing over one by just doing a change of variables in the path integral. All right? A change of variables in the path integral leaves the path integral invariant, and therefore this configuration has exactly the same, the same thing in the partition function as this configuration. So therefore, we have moved M2 over by one site, but left everything invariant. And now you can see that M2 is really topological because I just moved it over by one. Okay? If you imagine the full geometry, you can see that you can use this, of course, to not just move it over by one rigidly. You can really create any arbitrary curved thing within the constraints of the lattice by changing variables in the appropriate manner. Okay? So I encourage everyone to take some time to think about the geometry that makes that happen. All right? Okay. Because really, you see, actually every plaquette with whom U4 is involved will now have an action of G. And that's actually more complicated than it looks in 3D. In 2D, it will actually involve this thing going like, chew. If I do that here, it'll actually snake it around, but okay, you get the idea. It is fun to draw cubes and lines and see what happens. Okay, so this is the proof. Therefore, sorry, it's not M2 topological. The Google equivalent surface operator is topological. Okay, that's the end. Whew. Is everyone happy with this? Everyone believe me that this works. Okay. Good. So this is on the lattice, but now we can zoom out again. Okay. And if you now go to the continuum, these structures become more complicated, but this thing survives in the continuum. In the continuum, the distinction between the dual lattice and the other thing goes away, and in the continuum, you just get the G of M2 is a smooth topological operator. Okay, good. And that's the idea. Now, there's one thing that I've not done. I have not actually proven to you that the linking of this with the Wilson line gives you the same phase in this lattice construction. So the reason that it does is, imagine that I had a Wilson line going through here. Okay? If I was to move this thing through the Wilson line, then it's no longer true the path integral is completely invariant because the Wilson line sees this thing, right? It sees this link, and indeed you'll get an extra phase from that, all right? In exactly the same way as we did in the continuum, but here, in my opinion, it's a bit more well-defined. You can really quite explicitly see that the Wilson line transforms in the way that I said. So you can show that as well, and again, that's an exercise on page 27 that you can do. Okay. Any questions about this before we keep going? So I've proven to you, hopefully, yeah. Yeah.
So in the continuum,
yeah.
is there any construction that would be like parallel?
Yeah, there is. So let me just push on that a little bit, and then I'll come back to your question. So as you just pointed out, what we've really done is we've coupled in a two-form source. Let me just point out that this is one particular use of the two-form source, but there is a more general use of the two-form source. Okay. So let me just point out the general invariance of the two-form source. I've not actually told you that yet. So what is the most general invariance? So what you should do is consider now a Zn valued function. Consider a Zn valued function on the links. Okay, G sub L on the links. And assume this action, that it acts on the plaquette variables like this. UL goes to UL times GL. And the source B goes to GL dagger. I think I have my signs correct. This is the opposite of that. Okay. And so what's happening is I have some GL defined on the links. Okay. And it multiplies each of the link variables, and it works as a product on the plaquette source. Then this is an invariant to the path integral, and therefore Z is invariant under this operation. So if I call this B box prime, Z of B box prime is equal to Z B box. So this again is equivalent to the existence of a one-form Zn symmetry. Okay? So this is equivalent to the existence of a Gukov-Witten surface operator. These are the same statement. And now to come back to your question was basically, how do I do this coupling in the continuum? Is that right? This is surprisingly annoying because, you see, what we normally don't do is think about Zn valued fields in the continuum. Okay? Because what does that mean? You know, it seems like it's just fraught with discontinuity. You know, you're here and then at an interval point, it's a different value. So what you really consider is sort of global structures. Like if you integrate over some curve, you get some Zn element. And I'll talk a little bit about how to represent that structure in the continuum. You can do this in the continuum, but it's a little bit annoying. It's done in the appendices of various papers that I cite in these lecture notes. You can look at the paper on generalized global symmetries, the very first one. They do discuss this in some detail. I personally just find it a little bit clunky because the continuum fields don't want to be in Zn. What you do is you take a continuum object and you kind of Higgs it down so that it's in Zn, and this is a little bit clunky, in my opinion. Yeah. But the universal information you can still extract, though, using that operation. And this is just another way to get it. Yeah, it's a good question. Good. Other questions? Yeah. Okay. All right. Good. So now that we're completely convinced that we have a one-form symmetry, it's now time to talk about what the phases are. Okay. Now let's talk about confinement and one-form symmetry. Sorry. Someday. You can just say, Nabil. I think that's the most efficient way to do this. Yeah. Or the gong. We still have the gong, right? Anyway, so now that we know we have the one-form symmetry, we should now ask about the different phases. Okay, and by now we're really experts at this game, right? There are two phases, right? Number one, the symmetry is unbroken. What that means is the charged object, WF of C, the Wilson line in the fundamental, has an area law. This goes like e to the minus TP. I don't know why I'm writing a P there. T times the area of C. Okay? This is the unbroken phase, the one-form symmetry, and this is, of course, what we call the confined phase of non-abelian gauge theory. This is the ordinary phase, by which I mean this is what happens in nature. This is what this action naturally wants to do in 4 dimensions. Okay? This is what you generically get. And physically, again, what's happening is you are creating a Wilson line. It's creating a flux tube. The Wilson line creates a flux tube. That flux tube fills it in. The tension of that flux tube is this thing. Okay? All right. Now, the new thing that I just want to point out is that notice that if you inserted n Wilson lines, okay, then because this is a Zn symmetry, if you inserted n Wilson lines, then those n Wilson lines actually would not have an area law. Okay? They would end up having a perimeter law because n Wilson lines together is actually not charged under the symmetry. The conservation law is only a Zn conservation law, all right? Which means that n flux tubes can end, okay? That's maybe not completely obvious, all right? But it's a fact about non-abelian gauge theory. If you have a single flux, if you insert two external quarks, you have a single flux tube, it cannot snap. But once you insert n quarks, it turns out that n of them together can snap, okay? The existence of the thing that makes n of them snap is called the baryon vertex. This is roughly why baryons exist, okay? Okay. Good, so that's one phase. And the other phase is not this one. It's the one where the symmetry is spontaneously broken. So the SSB of this thing means that the Wilson line would have a perimeter law. You get the idea, minus some number times L of C. And this is the deconfined phase of non-abelian gauge theory. Okay? Yes? Yeah, sorry, always in the fundamental. Yeah. Oh, that's also fine, of course. If you take one in fundamental, one anti-fundamental, then again, of course, that's fine, yeah. Yeah, that's like a meson, exactly. And the important thing is the product of from the language of these lectures, if you take the product of those two things, that will not carry any net one-form charge, right? It's like WW dagger. It doesn't have any phase rotation overall. So that will not have an area law because it's not charged under anything, so why would it have an area law? Okay. And this is the deconfined phase in non-abelian gauge theory. This is slightly awkward. In 4 dimensions, gauge theories don't really want to be deconfined, but you can make them be deconfined if you add stuff and things. You want to make sure you don't add things that break the symmetry, which is the next thing I'm going to talk about. Okay. So notice one nice thing, though. You see, I started these lectures by talking about how gauge theory is mysterious and, blah, blah, blah. But from the point of view of the higher form symmetry, the confinement-deconfinement transition is really a normal symmetry unbreaking transition, all right? We have a global symmetry, it's unbroken or spontaneously broken, all right? So in the larger Landau paradigm that uses this higher form symmetry, it's a completely normal phase transition, all right? This is really the power of this thing, okay? It puts it on the same footing as the magnetization Curie transition in magnets. Okay, cool. So the next thing I want to do is discuss what happens if you add matter to the theory. Let's imagine adding matter. So it matters what representation of the gauge group we add the matter in. The most interesting thing is what happens if you add matter in the fundamental. So in the continuum, S now goes like, the action looks something like this. So imagine that I'm adding a scalar field in the continuum. So this scalar field, say I have phi I, which is in the fundamental representation. So this is in F. Then the continuum action looks like this. 1 over 2g squared, trace of f squared, plus d phi dagger d phi. Okay, integral d4x. And let's see. Has everyone seen this? Actually, maybe I'm going to leave that board untouched, I think. It's good to keep it there, I think. So I'll start erasing the other ones. So, so what happens is, when you add matter in the fundamental, is that actually you explicitly break the one-form symmetry. It's gone. Okay? So I want everyone to think about that while I erase the board. Boards. Yeah. Yes.
That's the one constant.
Yes.
Now we have that time.
Yeah.
So when you want this, then we get like a relative duality.
Yeah.
So if you do supersymmetry and work with extended supersymmetry to the symmetric angle, we get it as duality.
Yeah, yeah, yeah.
Does some other type of one-form symmetry also occur?
Yeah, so let's see, the case that I know the best is n equals 4 super Yang-Mills. If you start with SUN, n equals to 4 super Yang-Mills, then I believe if you do S-duality, what you actually get is the dual gauge group in the Langland sense. I barely know what that means, to be completely honest, but in the case of SUN, you get SUN mod ZN, which is different, different gauge group. The structure is different. It turns out you lose the one-form symmetry I just talked about because SUN mod ZN does not have a center, but you get a magnetic one-form symmetry, which is isomorphic. It's also Zn. And so it switches Wilson and 't Hooft lines, but the physics can be mapped from one to the other. Yeah. So there's a complicated and there's a beautiful story that makes this happen. Yeah. So you can think about this in great detail in under dualities, and many people have done this. So yeah, it's a very rich story. It's an excellent question. Oh, okay. Everyone has seen this board. Yeah. So I think I will still need all of them. I'll keep this, yeah. Mm-hmm. Yeah. Yes.
But in this case, the symmetry that is broken is a discrete symmetry, so you don't have that interpretation of the blue ones. So is there some way that you can describe the blue ones as Goldstone modes?
Really good question. I don't know, to be completely honest. Yeah, it's a really good question. I think that morally speaking, I think that's what they're trying to do, to be honest. Even though there's no theorem, I think that they're trying to realize this symmetry non-linearly, which is what Goldstone modes do. That's their role in life. So I think there's a sense where gluons are trying to do that. I get confused because I don't really know whether gluons deserve to have a sort of universal definition, because the truth is they don't really, they're almost an artifact of how we describe it, right? They don't exist at low energies. They're even in the deconfined phase, you don't see gluons running around. I'll talk about deconfined phase a little bit in a bit. So yeah, but I think morally speaking, I would love something like what you just said to be true. I don't know how to make it precise, or even if making it precise is useful, to be honest. Yeah, yeah, it's an excellent point. Yeah, good. Okay, so what I'm going to do now is I'm going to keep. So if you recall, I just erased this, but I added fundamental matter. And I claimed that really basically explicitly breaks the one-form symmetry. Okay, so I wrote this down in the continuum. If you add fundamental matter, yeah, yeah. So let me just write this down in words. Fundamental matter breaks the one-form symmetry. Okay, and what you mean explicitly breaks. It's just gone. It's not spontaneously broken. And you can see this in various ways. You can see it in the continuum. So I added some phi matter in the fundamental, right, just now. In the continuum, the way to see this is that here's my Grukov-Witten operator, and I have these phi particles that are running around and doing their thing. But every once in a while, a phi particle will go around the Grukov-Witten operator. And because phi is in the fundamental, when it goes around this, it'll pick up a phase now, right? And that phase is not one. It can see it. It's a non-zero phase. And therefore, the phi particles feel the Grukov-Witten surface operator, okay? They're not external probes. They're dynamical objects. Because they feel that, they will affect its existence in a way that makes it no longer be topological, okay? And that's how to see this in the continuum. And again, one can do this a bit more explicitly on the lattice. Okay, so let me explain how to do it on the lattice. On the lattice, what you do is, let's add the matter on the lattice, right? So on the lattice, what I'm going to do is, I'm going to introduce a field phi I on the sites. Okay? So here, phi I is in the fundamental of the gauge group, which means that under a gauge transformation, my degrees of freedom now transform like this. Uij goes like before, like lambda I, Uij, lambda j dagger. and phi I goes to lambda I phi I. Right? This is how it should work. Phi I is in the fundamental of SUN, transforming on the site, so it transforms to the matrix multiplying it in the normal way. And now I can write down a new action that involves the fundamental matter. Let me do that. So there is the regular kinetic term. And then there's a new term, which is now valued on the links, and it looks like this. Okay? So this term is valued on the links. So what's happening here, phi j u phi I dagger is gauge invariant by this construction. I get a lambda I dagger, lambda I dagger. So this is a gauge invariant term. And what this term does is, of course, it lets the phi I hop, right? It's a sort of hopping term between the links, the sites on the lattice, but it hops in a way mediated by the gauge field. Okay? This is the lattice version of the gauge covariant derivative. All right? Okay. So now, again, what we should do is now stare at this and ask, does this picture that I drew over here, does that picture survive, right, in the presence of this term? And the answer quite clearly is actually just no, it doesn't. All right? Remember before, I could just do a change of variables, u4 goes to g inverse u4, and it was a fine change of variables, and the only thing it did was move this g over from here to there. Now that doesn't work anymore because u appears in two places. It appears in the field strength, but it also appears in the hopping variable from phi going from here to here. Okay? And now if you do that operation, it will mess up that term. And it's just not invariant anymore. Okay? Fact. This is the lattice version of this picture I just drew of, the phi field, the phase, blah, blah, blah. That's really what's happening. This term just spoils the poor Gukov-Witten operator. Okay? This term spoils it. And therefore, it explicitly breaks the one-form symmetry. And what does that mean physically? So what that means is, if you have fundamental matter, there is no clear distinction between the confined and the deconfined phase. Okay? In other words, all Wilson lines will have a perimeter law because there's no reason for anything to have an area law. If you try to make a flux tube, say it's trying to be confined, okay? It's trying to make a flux tube, then you'll end up creating a quark-anti-quark pair in the fundamental that's break the flux tube. Okay? And therefore there's no area law anymore. And there's no sharp way to distinguish the confined and deconfined phase anymore. Okay? So you often hear it said there is no clear order parameter for confinement in QCD. This is why, because QCD has quarks, of course. All right? And this is a very interesting thing, that there's no distinction between confined and deconfined phase, because it means very crazy things can happen. So I'm going to not talk about it due to lack of time, but in the notes, due to a complete misjudgment of how much time I had, in the notes I have a section that talks about the Z2 gauge theory, okay? And I'm just going to tell you a little bit of the Z2 gauge theory because it's very simple, all right? The Z2 gauge theory has some phase diagram, all right? And I'm not going to tell you what the parameters are in the phase diagram, but there's one parameter which is like gauginess, gaugeness, and one which is more like matterness. And again, the notes explain what these things mean, okay? And it's a phase diagram that looks like this, all right? And what's happening is over here along this line, if you go far out, there's no matter because the matterness is 0, okay? And we have a confined phase of the gauge theory. And when you have a lot of matter, when matterness is very high, it turns out you have a Higgs phase of a gauge theory, all right? But the phase diagram of Z2 gauge theory looks like this, meaning you can go continuously from the Higgs to the confined phase. All right? And that's weird if you've learned things in the continuum like I did. Because, I mean, if you write down a Higgs gauge theory, it doesn't look like a confined gauge theory. But there's no symmetry reason why these two things should be separated, okay? Just like, you know, liquid and gas when it comes to water, there's no symmetry reason to be different, and in some models they are continuously connected, okay? In fact, the question for QCD is something people study quite actively. There were some very recent papers explaining that even though this doesn't work for QCD, there is some subtle way to understand the difference. So this is a thing that people really think about, and it's a really fascinating story, which you can understand very explicitly in the Z2 case, which you can look at the notes as an entryway into that if you're interested. Okay, any questions about this before I switch gears? Yeah.
Just what happens, so we looked at fundamental matter.
Yeah.
We add matter, let's say the adjoint.
Very good. So in the adjoint rep, the truth is we already have matter, sort of matter, in the adjoint rep because the gluons are in the adjoint rep. So they're already there. And basically that means that the one-form symmetry survives in that case. So what you need to do is just look at, for every rep, you want to basically see whether a term like this ruins your symmetry or not. Okay? If you did the same thing for adjoint matter, there'd actually be two U's in this formula because they come from either side. And there'd be U and U dagger, and therefore it would still be invariant under that operation, and so it survives. So you want to play a game like that. There's something called the n-ality of a representation, which really just measures whether or not it, like, you know, what is the overall phase under a center transformation. And you want your n-ality to be 1. And for the adjoint, or I forget how it's defined, but you want your n-ality to be such that it's trivial, basically, which it is in the adjoint, and it's not in the fundamental. Yeah. Excellent question. Good. Any other questions? Okay. Yeah.
Is this phase diagram that you just draw, is this what people are talking about when they talk about like moduli spaces and
So to be honest, not really, actually. When high-energy theorists talk about moduli spaces, then it's typically things are very, well, okay, it depends what you're asking about, I think, to be honest. But when most high-energy theorists talk about moduli spaces, I believe that you understand things at all points in the moduli space. It's like flat directions, which things can be continuously computed everywhere. This is not really the case. Like this phase is a topological phase, but things depend on the parameters very, very strongly here, and you can't really calculate anything. Yeah, so it's much, I'd say it's much dirtier than what most high-energy physicists say when they talk about moduli spaces. Things really depend on these parameters dramatically. Yeah. Yeah. Yes.
Does this diagram
Yeah.
basically mean that I can start from pure gauge theory and somehow start adding matter and do some other stuff and continuously go for confined to the Higgs phase?
Yes. That's exactly what it means. Yeah, that's exactly what it means. Yeah, yeah. Yeah. This is called Fradkin and Schenker Higgs confinement continuity. Yeah. So.
What's the other thing? Because if I
Yeah.
only add matter, I
Yeah.
guess I go vertically out.
Yeah, yeah.
What should I do to go slightly below?
This way?
The other way.
The other way. This is the strength of the gauge coupling. This is 1 over g squared. This is basically the two terms that are there are this guy and this guy, basically. Okay. Yeah. Yeah. Good. I can talk about this in the tutorial if people are interested, which it seems some people are at least. Yeah. I'm sure I can find a way to make it a series of exercises. Okay. Okay, good. So now I want to switch gears a little bit, and I want to talk about effective descriptions of broken symmetry. Okay. So some people had some questions about, basically, I interpreted the photon as the Goldstone mode of a spontaneously broken U1 one-form symmetry. We have seen that in gauge theory you have a spontaneously broken Zn one-form symmetry. And there should be an effective description of that low-energy physics. So I now want to tell you about that effective description. And this involves talking about a kind of topological field theory. Okay? These chalks are rapidly vanishing. All right. There we go. I have one piece of chalk left. So now this is basically the effective description of spontaneously broken one-form symmetry okay? And sorry, I should have said this is discrete one-form symmetry, so really it's going to be Zn one-form symmetry. And I'm going to do it in 4D, okay? But in reality, the 4D and the 1 form are not so important. You're going to see after I do it that you will be able to extend this to any D and any P by yourself, okay? So So this, for example, would, in principle, describe the deconfined phase of SUN gauge theory. I say in principle because, to be honest, all the ways I know of doing this, they kind of result in other degrees of freedom that kind of add extra bells and whistles that more or less invalidate this idea. But there are other, like, if you can look at ZN gauge theory, where this is really the right thing to use. And in 4D gauge theory, I think you can get it to work, but I've not tried that hard. It's not, 4D gauge theory doesn't really want to be deconfined in this way, but it's a detail. So what is the effective description of this? So we should first ask, what are the long distance degrees of freedom? Okay. So generically, all local degrees of freedom are going to be gapped. They're going to be massive, all right? Because there's no reason for them not to be, basically, all right? So generically, all local degrees of freedom are gapped, but what we do need to have is we need to have objects that correspond to the things that are charged under this symmetry. So what we need within this theory is the Wilson line, okay? And we need the Gukov-Witten surface operator, which is defined on M2, all right? And these two things need to do the following. They need to satisfy this linking algebra, which I'll write down one more time. It's e to the 2 pi I over n times WC. So I've made a subtle change of notation here. Previously, I had subscripts here for the fundamental and the center element and so on. But these are all just valued in Zn. So from now on, I'm just going to talk about the minimal element of each one, the charge 1 element in Zn. You can get the other ones by, taking these to the nth power, the kth power, okay? So this is the minimal Gukov-Witten line. This is the minimal charged Wilson line. And therefore, they have the minimal phase that has this k equal to 1 over here. Okay, good. So I need a theory that has all local degrees of freedom gapped, but it does have these surface operators in it, okay? And they have to have this topological linking. In other words, I need a topological field theory. Okay? So I'm now going to write down what the topological field theory is. So I need a topological QFT. And the thing that I'm going to write down is called BF theory. Okay? So I forget, this board is still available, right? Yes. Okay. So the theory that does this is called BF theory. And it has a really simple action. All right? So it depends on two gauge fields, which I'm going to call A1 and B sub 2. These are two gauge fields, and the subscripts denote the forminess of the gauge field, okay? So A is a 1 form, and B is a 2 form. And the action of BF theory can be written like this. It's equal to IN divided by 2 pi integral over M4 B wedge dA. It's called BF theory because sometimes people write this as F, and then the action is BF. Okay. So let me say a few words about this. This is a topological field theory, where here the word topological means that there is no metric involved in writing down this action. Okay? It's all forms. There's no star. Okay? There's no volume form. All right? You can write this down quite explicitly with no metric at all. What that means is the stress tensor is 0, all right? And it also means that this action is coordinate invariant without requiring the metric, which means you can do a diffeomorphism to move points around however you like, all right, with no notion of distance. And therefore, this cannot depend in any interesting way on local distances. It can only depend on topology. That makes it a good candidate to realize that, all right? Okay. A lot of people know about Chern-Simons theory. This is a kind of mixed Chern-Simons theory, okay? And here we have a 2 form and a 2 form, so this is okay for 4 dimensions. to generalize this to any number of dimensions, just change the formulas until it works, okay? And that's really fine. Okay. Now the action is invariant under the two gauge symmetries that you can imagine. So it's invariant under, this is a gauge redundancy. So you take A1 goes to A1 plus D of a scalar. Sorry, I should call this little lambda for later. And B2 goes to B2 plus D of a 1 form. The action is invariant under both of these gauge transformations, okay? To see this one, you might want to integrate by parts to put the D over there, and then it's invariant, okay? Okay. Now, an important fact is these are both compact gauge fields. What that means is if you take any 2 cycle, M2, and you integrate dA over that 2 cycle, so let me actually first write F equals to dA locally and H equals to dB locally. And if you integrate F over any 2 cycle, then you get 2 pi times an integer. And if you integrate H over any 3 cycle, you get 2 pi times an integer. Okay? This statement is part of the definition of the theory. You can view this as a normalization of the fields A and B. Okay? All right. Before I go on to say what this means, are there any questions about this theory before I go on to do something with it? Okay. Yeah. Just is playing a lot of things there. You are correct that the equations of motion of both A and B are going to be quite trivial. Yeah, yeah.
But yeah, so
Yeah.
if you vary this action with respect to B, then it looks like you get F equals 0, right? As a
Oh, yeah, yeah. Maybe this is a good time to do this, actually. The equations of motion are pretty lame. The equations of motion are, yeah, sorry, got it too. dA equals to 0 and dB equals to 0, right? In other words, both field strengths are 0, okay? And there are no local degrees of freedom. There are no propagating modes in this theory, okay? You know, you will still ask, but that's what we want. We want all local degrees of freedom to be gapped. You should imagine we're so far below the gap that you can't even see them. Okay, they're just gone completely. This is the extreme infrared of that description. All right. Now, however, there are global degrees of freedom, by which I mean that that linking algebra is realized. Okay. And let me. I'm going to talk about that, but first I'm going to talk about this parameter n. Okay. Yes.
So basically, I mean, even if you back integrate this,
Yeah.
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 Then I guess that F is not really equal to dA because then we cannot impose this condition. I mean, dA is 0 and F should be integrated to 2 pi z, etc. If it's not 0, then something is.
No, well, I mean, 0 is a perfectly good z, so it's okay. Yeah. You're right that you feel like you're not using it enough, right? You feel like there's things that we have missed out on, right? That's what you're saying, yeah. This equation is more or less correct. There's the possibility of having a non-trivial flux present is something that we have to think about carefully, and we will now think about this very carefully, yeah. Okay, but it's not localizable. It will be somehow extended over the whole thing. That's maybe the point of this. Okay, yeah. Okay, so I want to tell you about this parameter n for a second, because you see, I wrote down an action, and normally write down an action, you can just put a coupling there and make it whatever you want, all right? But that's not the case here. In this case, n is an integer. And I want to explain to you why n is an integer, okay? So, yeah, I can do this. Okay, let's, as an example as to why, let's consider the theory. We can do this on theory in any manifold. So I want to consider it on S1 cross S3. Okay? I'm studying the theory on this manifold, S1 cross S3. All right. Here's S1, here's S3. I'm studying it like that. Okay. Now, these are compact gauge fields. In other words, the gauge parameter is not really lambda, but it's exponential. E to the I lambda is the real gauge parameter. And let's do the following large gauge transformation. So this is a gauge transformation of the one-form field. I'm going to do a gauge transformation by e to the I lambda naught. Okay, so this is the gauge parameter. Again, the naught just means that it's a zero form, where lambda winds around the circle. Okay, so lambda naught winds around S1. In particular, if the S1 coordinate, if the S1 coordinate phi runs from 0 to 2 pi, so here phi goes around the S1. Okay, so if phi runs from 0 to 2 pi, I'm going to consider the gauge transformation where lambda naught equals to phi. Okay, so this is not single valued in terms of lambda, but it is single valued in terms of e to the I lambda, right? It's a perfectly fine gauge transformation. It is, however, not continuously connected to the identity. That's why I'm calling it large, okay? But it's still a gauge transformation. It is still a redundancy in states, all right? Is our action actually invariant under this transformation? So let me call A prime equals to the gauge transformed A, and B prime is, I'm not even transforming B prime, so let me not even write it, but B prime is the gauge transformed B. And now let me construct the difference in the action under this transformation. So if I construct the difference in the action under this transformation, note that I can't just do delta. It's not a small difference, okay? This is going to be a big difference because this really winds around once. It's a large gauge transformation. It's really a big difference, okay? And what is this? Well, this is going to be in over 2 pi. B doesn't change, but A changes by d phi, okay? So the change in A is d phi, and then, this you can write also like A wedge dB, which is how I'm writing it right now. I should have written it like that to start from, to be honest. These are the same action up to boundary terms, and it's sort of the boundary terms that we're stressing about now, okay? Not really boundary terms, but global structures stressing about now. So if I write this action as integral A wedge dB and not B wedge dA, then A changes as d phi, and dB is just h, this 3 form, okay? And I'm integrating this over S1 cross S3, okay? And now this only cares about the S1. Let me assume this only cares about the S3. That's an assumption, but let me just make it. What you find is that this becomes integral d phi on the S1 times integral on the S3 of h, okay? Which means this integral of d phi on the S1, phi is literally the S1 coordinate, so this just becomes 2 pi. So I get I times n times 2 pi over 2 pi, that goes away. And now my integral of h on the S3 is quantized to be 2 pi times an integer. So I get I n times 2 pi times an integer generically. Okay? Okay, this is fine, but it looks nice maybe, but it's also a disaster because it's not equal to 0, right? And so the action is not invariant under this large gauge transformation, right? Okay. So this seems really bad, all right? But the point is that actually, this is an intrinsically quantum mechanical theory, which sort of means that you don't care about the action itself. What you care about is the exponential of the action, okay? So we are going to be studying this thing in a path integral. So we're going to integrate over dA and dB, e to the minus s. And therefore, we don't care about the action, but it's exponential. The action is not invariant, but the exponential of the action is invariant. So e to the minus s is invariant if n is also an integer. Okay. So in other words, this theory only makes sense if the parameter n is an integer. Otherwise, it is not invariant under large gauge transformations. Okay. And so we see that this is actually a feature, not a bug, because we're trying to describe a spontaneously broken Zn symmetry, and so n should be an integer. So this fits. Okay, this is good. I'll just say that in general, this kind of thing happens whenever you have a topological field theory. Topological field theories are rigid objects. Okay, they just exist, and they should not have any couplings that you can vary continuously. This should always happen. And at a calculational point of view, it happened because, you see, this thing is not, the action, the local density isn't gauge invariant, only its integral is. And if you trace back what happened, that was related to why this sort of thing happened. And in general, whenever you have a sort of Chern-Simonsy term like this, you can expect some sort of quantization condition to happen. Okay, I am out of time. Tomorrow what we're going to do is we're going to finish this, and then I'll finish explaining that linking algebra, and then I will discuss non-invertible symmetries finally. Okay, great. I'll see you all in today's tutorial, I think. Thank you.